welcome back to school. Today we're starting our new unit, which is all about logarithms. But before we get into logarithms, we are going to review exponential functions. So we'll talk a little bit about growth and decay today, and we're going to be talking today about something called Euler's number. If you were here before Christmas break, we did an activity with M&Ms, which was one way of modeling or one way of introducing you to exponential equations and reminding you what those graphs look like. So if you were here for that, you will be very much ready for today. So we're going to first talk about exponential growth. So exponential growth functions look usually something like this. F of x equals a times b raised to the power x minus h plus k. So the transformations h and k in exponentials work a lot like they work with any other type of function, and h is with the x. It doesn't have parentheses around it, but it is with the x in that exponent. So that h value moves the graph left and right, and then the k value would translate it up or down, depending on whether k was positive or negative. Now we do have the restriction on b that b has to be greater than 1. So it could be 2, 3, 4, any number, and really it could be anything greater than 1. It could be 1.5. It could be literally any number as long as it's greater than 1. It could be a fraction that's greater than 1. So we'll start by just looking at the function f of x equals 2 to the x. This is a really basic exponential function. This function looks like the graph that is shown. A couple of things to notice about it. It does have an asymptote here. It's a horizontal asymptote. The equation of that would be y is equal to 0. And we can find the y-intercept easily. I mean, you can see on the graph it's at 1. But remember, anytime you're trying to find the y-intercept, you can find that by plugging 0 into the function. So we would, if we were just calculating it, we'd think to ourselves, well, f of 0 is 2 to the 0 power, which is 1. So the y-intercept happens at the point 0, 1. The domain of this function, well, if we're thinking about domain in interval notation, it would be from negative infinity over here. And then over on this right side of the function, that does continue to go outward. It's not having an asymptote in that vertical direction. It does continue to get larger and larger and larger. So it's from negative infinity to positive infinity. There is a restriction here on the range, though. It does not cover all values in the y direction. Our range, our lowest value, would be 0 here at this asymptote, and it does not include 0. It will never actually be equal to 0. But then, so it'd be, if we're doing bottoms up, it would be from 0 up to infinity for the range. All right, so let's look at a translated version of that function. So now we have f of x is equal to 2 to the x plus 4 power minus 5. Well, the base is 2. It's going to have the same basic shape, but we have a plus 4 here with the x. That means it's going to go left 4, and a minus 5 at the end here means it's going to go down 5. Well, I usually think about this vertical translation first when I'm looking at exponentials, because I think about this asymptote over here. Shifting this function down 5 means that the asymptote will move down 5. And then I'll focus in on this point here. This point is going down 5, 1, 2, 3, 4, 5, but it's also going left 4, 1, 2, 3, 4. So it's going to be here at negative 4, negative 4. And then you can just kind of sketch it from there. So the asymptote now is at negative 5. The y-intercept, well, it's in my drawing it looks like it's at 6, but we shouldn't just go by my drawing because it might not be very accurate. Remember that the y-intercept happens when y is equal to 0. So let's put that into our function. F of 0 is 2 to the 0 plus 4 power minus 5. Well, 0 plus 4 is 4, so that's 2 to the 4th power, which is 16 minus 5. It's actually 11. So my drawing is not even growing fast enough. It should be even more steep than it was. The y-intercept would be at the point 0, 11. Might be helpful, I guess, to find that before you graph it. Okay, so the domain here, think left to right, is from negative infinity to positive infinity. It's growing really fast, but it does cover all x values. And the range here is from lowest to the highest, bottom to top, from negative 5 to infinity. Okay, so you may be wondering, how does b affect the graph? How does the base of that exponent affect the graph? The two graphs that we looked at so far both had base 2. Well, the base just affects the general shape of the exponential. So they all have a horizontal asymptote. So they all have some kind of asymptote here, and then they grow, exponential growth. Um, the b value is just affecting the growth factor, how fast it's growing. So if you have base 10, that's growing really, really fast. It's very steep over here. Uh, this one has a base of 1.25. It's kind of hard to see. It's growing very slowly. Its growth rate is quite a bit lower. And any could be anything in between there as well. So the one we were looking at is the one on this graph shown blue, base 2. But you know, the base can be really anything, and it just affects how steep that graph gets. It's affecting the growth rate. But again, they all have a horizontal asymptote. So now we're going to look at exponential decay. Uh, exponential decay functions can be written a couple of different ways. You could see it like this first one, f of x equals a times b to the x minus h plus k, where b is between 0 and 1. So like this one, 1/3 is between 0 and 1. Another way that you could see it is written in the second part, f of x equals a times b to the negative x power plus k. That would be exponential decay if b is greater than 1. So you'll see it both ways, and it just, you know, it just depends sort of on the context. A lot of times in lower math, you'll see this form where b is a fraction, and once we get into higher math, we typically use this form with the negative exponent and b is greater than 1. So you could write functions either way, though. For example, this first one, f of x equals 1/3 to the x power. Another way to write that exact same function would be to say that it's 3 to the negative x power. Those two functions are identical if you graph them. They look exactly the same. The reason for that is because of the exponent rule with negative exponents. So if you have a negative exponent, that's the same as 1 over that exponent. And in this case, since it's a 1 in the numerator, that's the same as this. So those two things are really identical. Just two different ways of writing the same function. All right, so here's what f of x equals 1/3 to the x power looks like. Again, even when it's decay, it has an asymptote. For a base function that's not shifted up or down, that asymptote happens at y equals 0. The intercept here, again, that happens when x is 0. So if we plug in 0, f of 0 is 1/3 to the 0 power, and that's just 1. So our intercept is at 1, just like it shows on the graph. And then the domain, for domain, think left to right, so negative infinity to infinity. And for the range, bottoms up from 0 to infinity. So let's try graphing this one. F of x equals 1/2 raised to the x minus 1 power plus 3. So as far as the transformation goes, this is going to go over 1 and up 3. So I'm going to start by showing that asymptote shifted up 3. So the asymptote is at positive 3. And now I want to think about that 1/2 raised to the x minus 1 power. It's going to be a little different shape because the two bases are different. Let's think about the y-intercept. The y-intercept happens when x equals 0. So that would be 1/2 to the 0 minus 1 power plus 3. Well, that's the same as 1/2 to the negative 1 power. 1/2 to the negative 1 power is 2, which you could put in your calculator to figure out. So it's 2 plus 3, which is 5. Here is our y-intercept, 0, 5. And again, I find the y-intercept by plugging 0 in for x. All right, so I am going to pull up my calculator because a lot of times that's going to be the most efficient way to graph these types of functions is to look at your calculator and see what it tells you about the shape of the graph. Let's see, here it is. So we have 1/2 raised to the power x minus 1, and then we want to add 3 to that. Okay, so here is what the function looks like, and you can see on the calculator screen that it does have that asymptote we were expecting at 3, and it does have that intercept of 5. You can always use the table. If you hit second and then the graph button again, it will bring up the table of the function and give you all kinds of values which you could look at to graph. So it looks like it starts up really high, and then at 0 it has a value of 5, and then it gets closer and closer. You can see it getting right here closer and closer to a value of 3. These 3 points right here, negative 1, 7, 0, 5, and 1, 4, I can use on my graph to help me graph it nicely. And let me pull that back up. Here we go. So we had negative 1, 7, 0, 5, and 1, 4. And so it comes down and then just gets closer and closer to that asymptote. So the domain of this function, if we're talking about the x values here, that would be left to right from negative infinity to positive infinity. And the range would be bottom to top, lowest y value to the highest y value. That would be from 3 up to infinity. It doesn't include 3, so we use that parenthesis on that side with the 3. It doesn't include 3. It gets closer and closer and closer to 3, but it doesn't actually reach the value 3. Okay, so we're going to look at a little application problem. Decay is used quite a bit in science, and one of the ways that they use it is with carbon dating. So if Q is a mass of carbon, 14, in grams, whose half-life is 5,715 years, the quantity of carbon present after T years is given by this function, Q of T. So first of all, it asks, is this growth or decay? So the base of the exponential here is 1/2. So that will be decay. If you weren't sure, you could always look at a calculator to see that, to see if the shape is growing or decaying. But also you can get that information by looking at the base. All right, so it says determine the initial quantity. Well, the initial quantity, it's essentially asking for the y-intercept. It's asking you for how much you start with, and that's when t equals 0. So q of 0 is equal to 10 to the 1/2, let's see, 10 times 1/2 raised to the 0 over 5,715 power. Well, that's just 0. 0 divided by any number is 0. So it's 10 times 1/2 to the 0 power, that's just 10. So that's our initial amount, 10 grams. Now it says determine the quantity after 2,000 years. It's asking us what's Q of 2,000. well, that would just be 10 times 1/2 to the 2,000 over 5,715 power. And if we put that into our calculator, that would be about 7.85 grams, approximately. All right, so our next part, part D, asks us to sketch the graph over the interval from 0 to 10,000, over 10,000 years. Well, we've already got two of these quantities. At time 0, we knew we had 10 grams. And this is in thousands, so 2,000, the second amount that we figured out, is where t equals 2, because this is in thousands. So this 2 represents 2,000. That would be 7.85, so between 7 and 8. So you have 2 points here. And it's decay, so we could probably guess that it will, slowly go down. But I want to use my calculator here and graph it and show you how you can adjust the table and adjust the window of the graph to get a more accurate picture. So let me pull up my calculator. Okay, so we've got the equation now, 10 times 1/2, let me put it in parentheses, raised to the power, and we use t in our equation, we're just going to use x in the calculator, 5,715. Okay, so that's what our function looks like. Now, if I graph it, I'm really not going to see much because, yeah, I can see at the very top a teeny bit, because my window is not set to what I want it set as. So we're going to adjust the window, and our x values, I'm going to just put it from -1 to 10, count by ones. So if you look at this, it's counting, oh, I'm sorry, we want to count by thousands in the x direction. Whoops, where's my calculator? So in the x direction, I want it to go from 0 up to 10,000, and I want it to count by 1,000s. In the y direction, sorry, I was thinking about y direction before, I'm going to have it go from -1 up, whoops, go to, sorry, from -1 up to 10, count by 1. So on our axis, let me pull up the Smart, you can see that it went from 0 to 11. So my window will match that pretty closely. And now if I hit graph, it will give me a nicer picture here. Let me see, I'm going to change this to 11. Okay, so our y is going from 0 to 11 here. So this is what our graph is going to look like. And again, I changed it so that it's counting by thousands. Well, I could change the table so it's counting by thousands as well. Right now it's counting by ones. If that same button that has the window above it, you can see it says table set. So you can adjust the table. We'll start it at 0. So start means what it's starting by. And then this little triangle means it's a delta symbol. It means change. So it's what you want to count by. I want to count by thousands. So if I look at the table now, it gives me it adjusted by thousands. So it'll be 8.86, and we calculated that 7.85 a second ago. And so we can use these values. Sorry, I'm just jotting them down so that I can put them on my graph. Okay. And I will add them to my graph now. So the first starting quantity was 10,000. Then it goes down to about here. Year 3, it's really close to 7. year 4, it's down a little bit above 6. And by the 8,000th year, it's really just a little bit below 4. And here it's really close to 3. So here's the shape of the decay right there. Sometimes it looks almost linear depending on, how zoomed in or out you are. All right. So all exponential functions have a base. They all have a base. So let's look at these three and just quickly identify the base. F of x equals 2 to the x power is a base 2 function. Here, the base, it's 62 times 0.5 to the x power. The base is 0.5 or 1/2. This next one looks interesting. Sometimes people will think that it's a 5.3 to the x power, but this is 5 times 3 to the x power. It's a base 3 function. And then this one is base 10. Well, there's a certain base that comes up a lot in math and science, and it's so darn special that it has its own name and symbol, and it's called the natural base, or Euler's number, and the symbol for it is a lowercase e, and it's equal to 2.718281845904523, blah, 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 blah. Goes on and on and on and on and on. E is kind of like pi. They're both irrational numbers, so they have decimals that go on and on and on and never repeat or have patterns. It's really just a lot like pi. It's a constant that comes up a lot in math and science. So it's on your calculator. It's in 2 spots that you can find it. The first one, so pi is right here. E is just below pi. It's use the second button, and it's the division button. So it's right here. Or if you want e and raised to some power, it's over here, kind of by number 7 and number 4. Again, you have to use the second button for that. So e is found on your calculator in those 2 spots. We were just working with rational expressions, rational equations, so I thought it would be interesting to look at this cool function, f of x equals 1 plus 1 over x raised to the x power. This equation, when you graph it, its asymptote is located at the value e. So this is like 2.71828, blah, blah, blah. So that's one way that mathematicians define the number e. So evaluating expressions with ease, I essentially just want you to practice using your calculator to use that e button. So this is just a matching activity. So e to the 3rd power, if we ask our calculator what that's approximately equal to, it's approximately 20.086. If you're absent and you missed class, I encourage you to practice using this button. 4 times e squared is about 29.56. E to the negative 2 power is a small number, 0.135. 7 times e to the negative 1 power, which we could also write like this, is equal to 2.575. And 2e is about 5.437. So e, again, it's just a number. It's like pi. It's a constant. Sometimes we like to know about what it's equal to, what that decimal is, but sometimes we want an exact answer. Like sometimes when we're studying circles, we want to know that the area is 25 pi instead of saying it's around 77. So sometimes when we want an exact answer, we need to use our exponent rules to help us simplify. So on your paper, it has a review of those exponent rules. So if I want to know what e to the 3rd times e squared is, if I'm using my exponent rules, that's the same as e to the 5th power. 7 times e to the negative 1 power is the same as 7 over e. E to the 5th divided by e squared, if I'm using my exponent rules, that's the same as e to the 3rd power. 4e squared all raised to the 3rd power. Well, that 3rd power is applying to both the 4 and the e squared. So this would be 64, that's 4 to the third, and the e in this case is raised to the 6th power. Remember, when you have two expressions like this being multiplied together, we add the exponents. If it's a power raised to a power, we multiply the exponents. It looks a little funny. Okay, e to the negative 2 power times e squared. Well, this would be a case like that first one where we add the exponents. That would be e to the 0 power, and anything to the 0 power is 1. This last one is possibly the most tricky. I want to remind you of the exponent rule here, which is that radicals can be thought of as rational exponents. So this is a square root. It's a root 2. So that's the same as 25e to the 6x raised to the 1/2 power. Well, that 1/2 power applies to both parts. I'm going to go up high here. 25 to the 1/2 power and e to the 6x to the 1/2 power. Well, 25 to the 1/2 power is the same as 5. And for this part with the e, we would multiply those exponents. 6x times 1/2 is 3x. So it's 5e to the 3x power. Okay, so we can simplify expressions with e. Well, we could also graph using e as a base. It's a very common base for exponential functions. So the first one we're going to graph is basic function f of x equals e to the x power. So let's think about for a second if this is growth or decay. Well, e is the same as 2.71828 blah, blah, blah. So if we raise that to the x power, this base is greater than 1. So this would be a exponential growth equation. If you type that into your calculator, like shown on the screen here, e to the x power, your calculator will show you a screen that looks something like this. The y-intercept, which you could look at on the calculator and see, or you could look at the table, or plug 0 into the function, is 1. And the asymptote for this function, which you can kind of see here on both the calculator screen and on my big graph, is 0. It's not shifted up or down at all. It's a base function. The domain here in interval notation, if we're thinking about domain, that's left to right, from negative infinity to positive infinity. And the range, bottoms up. Lowest value is 0 up to infinity, not including 0. So that's the function e to the x power. And you can see, I just thought it would be interesting to look at, the pink function here is 2 to the x power. The red function is 3 to the x power. And the blue one is e to the x power. And it totally makes sense because e is 2.718. It's between these two other functions because e is between 2 and 3. Closer to 3 than it is to 2. So again, just affects the shape just a bit. So what if we had e to the negative x power? Well, e is a number greater than 1, so if we have a negative exponent here, that is going to show us some exponential decay. So if we type it into our calculator, like shown on the screen, and we graph it, it's going to look something like this. The y-intercept here, we could plug 0 into our function and we will find out that the intercept is 1. The asymptote, just like before, it's not shifted up or down. The asymptote is that y equals 0. The domain in inequality notation, domain is like what x values are okay in this function. And I'd probably just write it as all real numbers here. There's no restrictions on the domain. The range in inequality notation, that's when you're writing as greater than or less than. In this case, the y's, because it's range, the y has to be greater than 0. Okay, so we're going to look at just a couple of transformations with base e. So if I want to graph the function f of x equals 2 times e to the x power, we could type that into our calculator and graph it. it looks something like this. It looks a lot like e to the x. That 2 in front of it, multiplying it by 2, is just stretching it a bit. So if we want to know the y-intercept, we could plug 0 into the function. 2 times e to the 0 power is 2. So it has an intercept 2. Again, use your calculator to help you. You can see it on the screen here. And if you bring up the table, it's going to give you a lot of values that you could use. And you can see the y-intercept is on the table right here. At a value of 1, let's move that a little. At a value of 1, it's up to 5.4. So it's up here. And then we know that it's going to have the asymptote. You can see on the screen the asymptote is really close to 0. So just kind of make sure you get at least one good point on your graph. Make sure your asymptote is in the correct spot. And then sketch, this basic shape. So the asymptote here was at y equals 0. The domain in inequality notation, we would probably just say it's all real numbers. There's no restriction. But the range here would be y has to be greater than 0. It's a y because we're talking about range values. And those range values, those y values are all greater than 0. So that's 2e to the x. Another one, e to the negative x plus 4 minus 2. So if we type that into our calculator and graph it, it looks something like this. It's exponential decay. It looks like it got shifted forward, or sorry, to the right 4, which maybe is different than you thought because it says plus 4, but it's somewhat complicated to explain why that's happening. That's why on a lot of these functions, use your calculator to help you graph it. So it does shift to the right 4 and it shifts down 2. So you can see on the calculator screen that asymptote is at negative 2. And on the table, you can see that it's getting closer and closer to negative 2. The y-intercept is not shown on the table. It would happen when x is 0, so we can plug 0 into the function to find that y-intercept. E to the negative 0 plus 4 subtract 2. Well, if we have our calculator calculate that, it is about 52.5. 52.6, I guess, if I round. So that's definitely not showing up on our graph here. But I can see this nice point on the table to use for negative 1. And at 2, it's at about 5.4. So I like to use the table a lot to graph these. And so it's coming down and then getting closer and closer to that asymptote. Ooh. So the domain in interval notation left to right, negative infinity to positive infinity, and the range bottoms up from negative 2 to infinity. All right, one last graph and then we're done. Negative e to the x plus 3. So if we type that in, that negative in front reflects it. It was an exponential growth equation, but it got flipped upside down. So it's not technically exponential growth or decay. It's a reflected exponential function. So it does shift up 3. We can see that in both the equation and the graph. So the asymptote is at y equals 3. On my table, I can see here the y-intercept of 2, or I could find that by plugging 0 into the function. So it's negative e to the 0 plus 3. That's negative 1 plus 3, which is 2. And we can see from the equation that it starts up really close to that asymptote, and then it just decreases very quickly. I didn't really decrease quickly enough, but I want you to have at least one good point. I want your asymptote to be clear. I'm not going to be super duper picky about the exact shape of your function. So the domain in inequality notation, the domain would be all real numbers. We don't have any restrictions on our x value, but the range here is interesting. If we're writing it as an inequality, we're thinking about, are the y's bigger than a certain number or lower than a certain number? In this case, y has to be less than 3. And that is it for today. So we reviewed how to graph exponentials, and we introduced a new base, which is the number e, Euler's number, which is 2.71828, etc. So that's it for today. The homework assignment is there in your notes. And the answers aren't on that homework paper, but you do have the answers on the back in the back of your packet at the very end. So you can check your work, and next time we will actually jump into the logarithm part of the unit. That's it for today.